Thank you for joining us for this broadcast of Science and the Solar Eclipse. I'm your host, Gordon Dickson. Thanks again for joining us today. We are talking about the really interesting connections with understanding science through a solar eclipse and the things that we have discovered, that scientists have discovered over the years. We're talking to Dr. George Matzko again. Dr. Matzko, thank you for joining us today.
Thank you for having me.
You actually saw a total solar eclipse in 2017 in Greenville, South Carolina, and you were describing the really interesting shadows that developed around you there on the Earth because of that. Tell us a little bit more about that, because this was very intriguing.
Well, while everybody else was looking up with their eclipse glasses, looking at the eclipse, I was, for some reason, looking down on the ground, on the concrete in front of me, and I saw these shadow bands, sometimes known as shadow snakes or shadow waves. They're transient, wavy patterns of light and shadow that appear on the ground just before and just after totality during a solar eclipse. And when we talk about this, really what we're talking about is studying the Earth's atmosphere using solar eclipses. Mm-hmm. So let me go back and explain that. So during a solar eclipse, you have a sudden decrease in incoming solar radiation. You get this noticeable drop in temperature in areas experiencing totality. And we can measure the temperature changes using ground-based thermometers and weather stations. And so that's interesting. But also we see atmospheric effects when we look at the sun spectrum intensity during different phases of eclipse. We see atmospheric phenomena like absorption, scattering, refraction of the sunlight. And that's where this business of the shadow bands comes in. During totality, observers may witness phenomena such as air glow and shadow bands. Now, air glow is a faint luminescence caused by chemical reactions in the upper atmosphere. I didn't see those. But the shadow bands are these wavy patterns on the ground that look like snakes. They look like snakes to me, writhing on the ground. And it's caused by atmospheric effects. And because of air density fluctuations and turbulence, the shadow bands are actually caused by the refraction of the sunlight passing through the Earth's atmosphere. So here, the Earth's atmosphere, you have a sudden change in temperature. You know how when you're in a very warm place, a desert and so forth, sometimes you see a mirage, and that mirage is the wavy, the heated air above the hot sand rising up, and it looks like water to us and so forth. It's kind of similar to that, where you're having the air heats up and then cools back down because of the totality, and because of the way the light is refracted through the air, it forms interference patterns. These shadow bands or shadow snakes are interference patterns when the refracted sunlight reaches the Earth's surface. And so you get areas of dark and light on the ground, and they wave. They appear to be like snakes moving along the ground. So just very, very interesting phenomena, and I was glad to be able to see it back in 2017. So I recommend to your listeners, if they're in an area of totality, that instead of just always looking up, look down for a little bit just before totality, just after totality, and you'll see these shadow snakes on the ground.
Now, this is an especially intriguing discussion because in previous broadcasts, we've talked a good bit about what we have learned about the sun and the stars as a result of a solar eclipse and the observations during a solar eclipse. But you're pointing to the fact that we have also learned a good deal about the Earth's atmosphere during a solar eclipse. Is that right?
Yes, that's right. So you see these refraction patterns that we call shadow bands. We can also study the Earth's ozone layers, for example. A significant portion of the sun's UV radiation is absorbed by the ozone in the upper atmosphere, and we can actually understand something about the distribution and thickness of the ozone layer during a solar eclipse. That's important. Also, ionospheric effects. Sudden decrease in solar radiation during an eclipse can cause an effect of the ionosphere. That's the region of the Earth's upper atmosphere where ionization occurs due to solar and cosmic radiation. Scientists use radio wave propagation measurements, satellite data to study the ionosphere changes during the eclipses, and helps improve models of ionospheric dynamics and space weather prediction. Mm-hmm. So eclipses provide many valuable opportunities for atmospheric scientists to study all sorts of aspects of the Earth's atmosphere: temperature variations, atmospheric optics, ozone distribution, ionosphere behavior. And when they analyze the data during eclipses, they can deepen our understanding of atmospheric processes and their interactions with solar radiation.
And I know that, let's take radio stations. There are still radio stations that only broadcast during the day because of this effect that you're talking about. And later on that same frequency, you'll hear a much more distant radio station. How is that connected to the changes in the atmosphere?
Right. So the ionosphere, the lower parts, are only there during daylight and disappear at night. So you can actually measure where that ionosphere is, in other words, where the boundary is, based on day and night. And the radio frequencies can bounce off those lower layers of the ionosphere, or be absorbed by the lower layers of the ionosphere. When at nighttime, when the number of charged particles in the lower layers drop, some of the radio waves can travel higher up into the ionosphere before they're absorbed. Mm-hmm. So instead of bouncing off the lower layers, which ultimately shortens the distance they travel, the signal can bounce off both the lower and upper layers, allowing them to be transmitted across longer distances, and while still being heard short distances as well. So for example, I was talking to someone who works at the Caribbean Radio Lighthouse, where they're sending out the gospel all over the world. And they were talking about how they have quite a few listeners in Finland, listening to the gospel in Finland being broadcast from the Caribbean Radio Lighthouse. And I thought, how's that possible? Well, it's possible because of these radio waves bouncing off different layers of the ionosphere before being absorbed, and allowing people at great distances to hear this radio station.
All the way from Antigua, if I'm remembering correctly.
That's right, Antigua, that's right.
You mentioned
Finland.
Yep, that is remarkable. You mentioned once before that light waves are self-propagating. Is the same thing true with radio waves? I understand that they're absorbed, you talked about, in the atmosphere and, of course, by the Earth. But are radio waves, as part of the electromagnetic spectrum, are they also self-propagating?
Yes, all the different kinds of electromagnetic radiation. Radio waves, microwaves, infrared, UV, gamma rays, X-rays, all of those are all self-propagating. That's true of all kinds of electromagnetic radiation.
And this explains why they have the very large antennas trained on various parts of the universe. I mean, and they're able to actually receive those radio waves across such vast distances because those radio waves are self-propagating.
That's right. And unless they run into something and get absorbed, they're going to continue on indefinitely, into the outer reaches of outer space. So they're hoping with like the SETI project to pick up on, some alien species radio programs, probably, doing a comedy show or something. I don't know. and
the shadow knows.
The shadow knows. That's right. Amos and Andy or something. Anyway, they're wanting to actually pick up on radio broadcasts from alien civilizations, with the idea that if we developed radio and then TV and so forth, and they are broadcast into space at the speed of light, then other civilizations have done that as well. Of course, I don't think there are other civilizations. The Bible makes it clear that we are the center of God's creation. And now, unless you're talking about angels, and I don't know if angels have radio broadcasts. I don't think we're gonna pick up on any of these signals. So far, it's been a dud. They haven't discovered anything. They haven't listened in on any alien civilizations out there broadcasting to us.
You referred to it a moment ago, but these radio waves, other parts of the electromagnetic spectrum, they move at the speed of light. Is that correct?
Yes. That's right. All of them move at the speed of light. They all have that in common.
And so it's always a constant, so that even if the source were moving toward us, that would not make it go any faster.
That's correct. And has to do with relativity. So Einstein had this great idea, is that the speed of light is the same in all inertial reference frames. And so that great principle is true. In other words, if you put a flashlight on the end of a rocket and shot it at great speed, the speed of the light would still be the same. It wouldn't add to the speed of the light. The speed of light is the speed limit of the universe, as far as we can tell.
And therefore, it would not detract either. If the object were moving away, it would not subtract from that speed.
That's right. So the speed stays the same. What differs is the frequency. So as it's moving away from us, it gets redder and redder. The waves spread out, and as it's going toward us, it gets bluer and bluer. The waves get scrunched together. It's the same, but the difference between the crests and the troughs of the waves is what changes.
I know that with respect to sound, the study of sound, we refer to the Doppler effect. Would it also be called that when you're studying light?
Yeah, we call it more redshift. We talk about the redshift, but it's the same principle, basically, is that the frequency depends on whether you're going toward the source or away from the source. Just as you hear a train whistle, a train coming towards you, you hear a higher frequency, and then the train goes past, you hear a lower frequency, the pitch lowers. So in sound, we talk about the changes in pitch. In light, we're talking about changes in color. They're very similar to the Doppler effect.
Yeah, that makes sense. Well, once again, we'd like to thank you all for joining us today. We hope that these conversations have been interesting. I know I've been fascinated by what we've been learning here. Dr. Matzko, thank you again for joining us on the broadcast today.
Thank you very much.
Thank you again for joining us for these series of conversations with Dr. George Matzko. He can be reached at his website, georgematzko.com. That's GeorgeMatzko.com. The Matzko Science Ambassadors. These broadcasts are brought to you by LiveServeLead.com. Live, Serve, Lead, helping others succeed.